Yeah. The max from infinite series. I don't know that. The side of communicate homework.
Yeah, I know it's a lot. I know it's a lot. But you can, I mean, I'll post the answer key to this, and I skip a lot of them, like because I used to do like every other problem, just so that you guys would have to do something. But since I'm not grading this, you could do as many as I do. And then if you're like, I still don't get it, then do more. Like do these for you. Okay, but let me say this. You guys said Tuesday's probably too soon for Unit 9 test, which I think I agree. I think we could do it Wednesday while everybody's doing a study hall. That might make more sense. And then I had a plan to like do the VC questions on the Unit 7 packet that I'm going to give you later. And we can just figure out if we can do those or if you just do them at home or what. But yeah, like I said, I think the Unit 9 test, like feeling like you have to know it is important because it makes you like learn it for real. So let's do that Wednesday test rather than Tuesday test. Okay, and then let me introduce this new thing, which, like I said, is I think like one of the more interesting things we learned and the most like it makes you think hard and I don't know. I think I have a fun time teaching this and learning this when I was your age. Hopefully you think the same, but it is kind of tricky. It's like it's not easy. So here's the idea: is I mean, you can see an infinite series. The like motivator for all this is like, is there ever a time where I can add an infinite number of numbers forever and get a finite answer? Yeah, so I was thinking, should I even ask them, or is that an obvious question? I mean, here's the thing: if I ask you, is there ever a time when I can add an infinite number of numbers and get a finite number? I think your intuition, if there wasn't a whole packet that I just gave you studying the infinite series, if I just asked you that at the beginning of the year just for fun, you guys would probably say, no, you can't do that. If you add forever, you eventually got to get enormous. You got to go to infinity. But yeah, no, it turns out they can. And here's like a simple example. What if I did 1 and then I added 0.1 and then I added 0.01 and then I added 0.001 and then so on and so on and so on and so on. If I did that forever, I'm never going to get to infinity. I'm just going to keep adding to the right of the decimal point. Here's like a simple series that will never go to infinity. This will become a finite thing. You know what I mean? Like there's a very, very, very like the one I came up with off the top of my head. I'm adding numbers forever. This is 1 plus 110 plus 100 plus 1000, etc. There's me adding an infinite number of numbers, but I got a finite answer. So yeah, we have a bad intuition. We as humans have a bad intuition on how infinite things work, because like we don't normally work with like infinite things. And so this is a little bit hard to get into and to get an intuition for. But you'll see as we go through the notes, I think you'll start building an intuition and be like, oh, this feels like it should converge. This feels like it should diverge. You'll gain a bunch of tools for doing that. So let's get into it. Watch this. First part is kind of just it's first vocab, I guess. It says the sequence is an enumerated collection of objects called elements or terms. A finite sequence is denoted as follows. I don't think you need to know this right now at this level, but here's like a sequence. Again, sequence is just a list of numbers. Here's the first one, here's the second one, here's the third one, etc. Here's an infinite series where it goes to infinity. It doesn't stop. It doesn't stop at the nth one. Uh, if they have some sort of limit, like as you get farther and farther, as you keep progressing down the list, if all those numbers are approaching one thing, then we call that the limit. And we say that it converges if this is a number. Otherwise, if it doesn't converge to one particular thing, if it keeps alternating between 1 and -1, or if it goes to infinity or whatever, then we say it diverges. All of these words will come back later. That's why I'm going through them fast, but here's a sneak preview. All right, so that's sequences. Sequences are just lists of numbers. Series is like you add all these together. So series is just a sequence, but you add all the terms. And then a partial sum, like if you have an infinite series, here they are, what the first term plus second term plus third term, whatever, all the way to forever. Partial sum is like, for example, the third partial sum will just be the first three terms added together. This will become important in a second. And then it says, we say that an infinite series an infinite series converges if the sequence of partial sums converges to some number s. You'll see what that means in a second. If the sequence of partial sums diverges, then we say the series diverges. Again, you'll see what that means in a second. So watch this. Here is a series, really similar to the one I was writing actually on the sideboard, where you're just adding the odd numbers basically, starting at 3, then 5, then 7, then 9, etc. And you add them all the way to infinity. It says find the first 5 terms of the sequence of partial sums. So not the first 5 terms of the sum itself, like not 3, then 5, then 7, but 3 plus 5 plus 7, etc. So what I mean is the first partial sum would just be the first term of the sum. So if I plug in 1 into here, I'll get 2 plus 1, which is 3. Okay, done. There's my first partial sum. All right, my second partial sum would be 3 plus 5, which is 8. So that's what I mean. It's not 5, it's 3 plus 5. Third partial sum would be 3 plus 5 plus 7, which is 15. Circle these results. Fourth partial sum would be 3 plus 5 plus 7 plus 9, which is 24. And then fifth partial sum, 3 plus 5 plus 7 plus 9 plus 11 is 35. Nice. Okay, cool. And then it says, does the sequence of partial sums converge or diverge? As in, if I take these numbers, 3, then 8, then 15, then 24, then 35, do they look like they eventually will slow down and reach a particular number? Yeah, okay, good job. Good job. Everybody's saying no, of course not. So no, let me say this. Let me say it like this. Limit as n goes to infinity of these partial sums. Looks like it goes to infinity. Therefore, it does not converge, it diverges. It would converge if this was equal to 123 or some finite number. But no. Okay, and then on the next page, you get asked basically the same thing, but just subtly different. So here we were asking, take this as its own sequence, 3, 8, 15, 24, 35, etc. Take that as its own sequence. Does that converge or diverge? The next page asks, does this sum, based on what you just found, does that sum converge or diverge? And it's basically the same question because you're just getting asked, does this sequence converge? But the wording of it is different so that you see what the definition is. This sum would converge if this converges, and it would diverge if this diverges. So if that was like, I don't see the difference there, I don't think you need to stress about it that hard. It's basically just asking the same thing twice. Does the series converge or diverge? It diverges because of what. Okay.
It's like a correlation between those two.
It's like the way it's defined, whether a series, if you get this series from 1 to infinity of just anything, this guy converges if you take finite ones, like you go to the 100th one, then the 101st, and the 102nd, and then you see if those sums converge, diverge. So the way it's defined is this will converge if the partial sums converge, which is what it was asking. Do these partial sums converge? No. Okay, so therefore, does the series converge? No. That's what I was trying to say. Okay. And then part D says the series in this example is an arithmetic series, the terms of which are being determined by adding some constant amount to the term before it. So we started with 3, then went to 5, then went to 7, then went to 9, etc. So we're adding 2 to each term each time. Okay, that's what arithmetic means. And then it says, do you think there are any convergent arithmetic series? So can you think of one that might converge? Or can you think of a reason why no arithmetic series would ever converge? Okay. What do you think? Yeah.
I mean, if you can subtract, then you can just do like n-1 and all it be 0. But if you can't subtract, then I don't think it's possible to be just always be increased.
9. What do you think?
Would it be possible if you had the variable on a denominator?
Then that's not arithmetic because then you're adding less each time. Good job, you guys. Yeah, that's exactly like the only way that could happen is if you're doing something that's not by definition arithmetic. So, do you think there are any convergent arithmetic series? No, no way. Couldn't happen. Because what Jeremy said, it's linear. So, like, no matter how little the slope is, eventually your terms themselves are going to get enormous. And then take all those terms and add them together. That's going to get enormous too. So, I don't know that there's. I could write more if you wanted me to, but I don't think it's necessary. Like, even if you had, like I'm saying, even if you had a tiny series. Pretend that's 1 million. What is that? Oh, that's exactly 1 million. Okay. 1/1,000,000th times n. Every million terms, you're going to be adding one whole number to that. And you're doing that forever. So no, these will get enormous. No matter how small you try to add, they'll eventually outgrow it. Yeah? Okay, all right. So then good intuition right off the bat, you guys. Good job. All right. But that's for arithmetic series. But are there ever series that converge? Well, the answer is yes. Otherwise, we wouldn't be studying, like I said, eight different sections in this unit. One of the ones that converges are called geometric series. And geometric series are ones that look like this. Basically, number times number to the k. Where a is the first term in the series, and a is in 0, and r is the common ratio, where, like, to get the next term, you're multiplying by the same amount each time. Like arithmetic series, the one we were just looking at, 3, 5, 7, etc., we were adding the same amount to get the next term. This one is multiplied by the same amount to get the next term. And it says geometric series will diverge if r is bigger than or equal to 1, and if r it's just less than or equal to, but this should take this strictly less than. If r is strictly less than 1, then the series converges to that sum. Yeah, okay, so let me leave it there. Take my word for it. If you want to see how or why or how these were proved, I can show you. But let's see how far we get today, and then if we have extra time, I'll show you like why this is true. But for now, take my word for it. Geometric series converge if the ratio is small. So it says determine whether the following series converge or diverge. Okay, here's one, 3 over 2 to the n. Wait a second, hang on. I told you arithmetic series look like number times number to the k. This does not look like that. So, oh, you see what? Oh, this dude,
Yeah.
but then it doesn't apply to the 3.
Change word.
Yeah, it's actually maybe something that you would not have thought of yourself unless you see this trick once or twice. Do you see how to rewrite it like that? Oh, okay. Oh, okay, nice. Yeah. That's what you were saying, I see.
Yeah.
But I thought you meant the whole 3 halves to the negative end.
Oh,
Yeah, no, this is what you and Annika were saying. Oh, the other ones. All borders. And then let me get myself statement. Three times 2 to the negative n, or just to make it very, very clear what this r is, I'm gonna make it instead of 2 to the negative n, I'm gonna make it 1/2 to the n. Because then 1 to the okay, fraction to the n means top to the n and bottom to the n, but 1 to the n is always 1 anyway. So this is the same thing as that. And then the reason I'm writing it like this is because it's very, very clear. Here's my first term, a, and here is my common ratio, 1/2. And so according to this, since r is smaller than 1, this should converge. Nice. Yes?
I mean, do you have to do that, or do you just look at like the equation and see that like 2 to the n is always gonna, not always, but like after 1, it's always gonna be bigger. It's gonna be bigger on the bottom for the most part.
Yeah, but that's not enough. But that I know what you're saying, but that's not enough. There's a series, you'll see this later, but this series right here, again, like I said, you guys are seeing this for the first time ever in your life, and so you don't have like you haven't built up enough. You haven't seen enough examples to like know what's going on. But this one looks like it should converge because this should get smaller and smaller and smaller and smaller and eventually gets very, very, very small, but it actually doesn't. So it's not enough to see, well, it's not enough right now to just look at this and be like, this will get small, so therefore it converges. It doesn't always work. Like I'm sure you get. Okay, so this one converges, and I think it's important to see because later you'll get asked this a decent amount. So what does it converge to? Like if I add these numbers forever, what will my answer be? What will my sum be? People smarter than us figured out that it would be this. And it's actually kind of cool to see where this comes from. But we'll see if we have time at the end. But what will this converge to? Let us check. The answer will be n equals 1 to infinity. And it says it should be a here strictly. But really this should say like the first term in your actual sum, because this sum only applies to things that look like this, where they start at 0, whereas ours start at 1, or the powers, or it starts at 1, but the power is subtracted by 1, and that's not the case here. The really it should say first term there, as in if I plug in 1. If I plug in 1 into this sum, I would get 3/2. That would be my first term. With me? Plug in 1. Okay, so then it would be 3/2 over 1 minus r. And the common ratio here was the 1/2 that we agreed on. That would be our sum. And if you're trying to figure out what that is, that would be 3/2 over 1/2, what would be 3, right? 3/2 over 1/2. Because you keep taking it or you cancel the 1/2, that's 3. Okay, which is kind of cool. That means if you take numbers like this and you keep adding and adding and adding and adding forever, you get an answer of 3. And again, if I have time at the end, I'll show you where and why that is the case.
It's kind of like asymptote.
Yes,
Okay.
but the asymptote for
Yeah.
the partial sums,
Yeah.
not for the actual term themselves. Because the terms will get tiny, they'll go to 0. But the sums will get closer and closer and closer to 3. Nice.
But this one will touch.
No, no. More like it'll get so close to 3. Well, I mean, I'm saying no because you'd have to go forever, literally forever. You stop at 3 quadrillion, it wouldn't be exactly 3, it'd be 2.99999999999. But so many nines that it's essential. Yes.
But this is still pretty similar to like limit and.
That's it. Yeah, that's exactly it. That's why I'm saying essentially it is 3. It can get as close as you want to 3. If you want to be 0.000000003 quadrillion zeros and then like be within 0.00001 of 3, then you can be. You just have to go far enough. Meaning this will just approach 3 forever. Yeah, nice. These questions that you guys are asking are like have to do with the actual big definition, like actual formal mathematical definition of what it means to be a limit, which is fancier than you guys saw. But it's basically what I'm saying. Nice, y'all. Good question. Okay, anyway, that one converted. This next one, 3 halves to the k. That one, like if you want to write it like we did the other one, where there's a first term and a times r to the k, you could write it like that. Here's my a, here's my r. You look at that r and you're like, no, this diverges because why? Yeah. This diverges because this is greater than 1. The r, the number with that. I don't know how to do it. This diverges because of that. Nice. All right, cool. What time is it? 28. Okay. Consider the infinite geometric series where now we're not given the term. It says just some geometric series. I know this is geometric. All the terms are positive. And the first term of the series is 108. And the third term is 12. And then it says determine the value of the series, as in if I add forever, what's my final answer, like the one we just did. Okay. So it goes 108 plus something plus 12. And then plus keep going in that same pattern, blah, 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 blah. And then what does that equal at the very end? Time is it 28. I think you guys can handle it. It's geometric, meaning did you guys catch what that meant? Like to get each next term, you multiply by the same amount. It tells you it's geometric. Find what each time. Okay, let me leave it there. You guys think. Uh, 12 divided 108 divided by 9.
Oh, how it? Wow, that was good. Holy crap. Oh, that was good.
Oh,
That was good.
yeah. Let me check my key. I think you're right.
Holy crap. I found it. Found it.
Okay, now, yeah.
I didn't look at it. I'm like, oh, that looks like a dumpster. And like, I just
Good job, y'all. Yeah, good job. But then did you guys find the answer? Like what is,
Um,
if you add forever, what do you get?
But I think that would.
It should have been. But as written, it can't because you're multiplying by taking each other. So this would be like x squared.
Okay. Oh,
Yeah, not 2x, but x.
so one nice.
That's, yeah. Okay. So first of all, good job coming up with the common ratio. If you did, I saw some people did. You're trying to figure out, okay, from here to here. Oh, I shouldn't have done that one. It's gonna take a while to load. But the idea, okay, wasn't that bad. You're thinking, what did I have to multiply 108 by to get to 12? In other words, what's 108 divided by 12? Oh, that's 9. So if I multiply by 9 in two, or like, if I'm dividing by 9 in 2 slots, then each slot must have been divided by 3. So that's why people were saying this is times 130. In other words, 108 times 1/3 is 36 times 1/3 again gets me to 12, and then times 1/3 times 1/3 times 1/3. So that the sum looks something like this. And equals 1 to infinity, my sum would look something like 108 times 1/3 to the n. Okay. I'm about to edit that in a second, but let's just actually no, I can't get the sum unless I edit this. The way I wrote it is actually kind of wrong. Because if I plug in 1 into here, which should give me the 108, it actually gives me 108 times 1/3 to the first. So it gives me the 36. So I need to shift it over by 1, like exactly. Either start it at 0, good job, or since this said start at 1 and go to infinity, just to make it match that, let me see, n minus. Good job, you guys. Yeah, you guys have great intuition already. Cool. Okay. And then now, if I'm trying to get the sum, first of all, we agree that this converges because it's 1/3. It's less than 1. So then this would equal first term, which only was 108, over 1 minus the common ratio. And then I didn't even get what that was. Circle. What is it?
62, but that doesn't make any sense. But it's
You're dividing by 2/3. So I have to get bigger.
no. I'm like for the sequel.
You're saying 160, it only goes up to 162 and it starts at 108. Yeah, but it gets small so fast. 108 plus 36 is whatever, 140 something, 150 something. And then you're still gaining like 11 or 12, even as you're adding smaller and smaller fractions. But that's what I mean. We have no I agree with you that I'm like, wait, 152 when I'm adding 108 plus 12 plus 36 plus the next one would be 4. Yeah, it's kind of wild to wrap your mind around these infinite things.
Yeah.
But that's what the math tells us. Okay. So geometric series, super important. Keep those in the back of your head. Those will be like a baseline to compare other series to. Like, is this growing faster or smaller than the geometric series? In which case, that I'll say that this converges or diverges. Very important. Very good baseline thing. Another way to tell if something is going to converge or diverge, if it doesn't look like a geometric series, which is the only thing we know right now that converges. Another thing we can do is the nth term test for divergence, which I don't even think I have to teach you, but here it is with a name. It basically says, well, there's what it says formally, but basically what it says is that if your terms aren't getting small, like if your terms aren't going to 0, the terms itself, then it has no chance of converting. Formally, what it says is that if the limit as n goes to infinity of each term in the sum isn't zero, like if it doesn't eventually go to zero, then this series diverges. Okay. Now, question for you. When did you hear me say that if it is zero, then for sure it converges? Never. I never said that. The example is like the one that I told Eden. This series gets small, gets very, very small. It goes to zero, each term does. But it actually diverges. So this doesn't say if the limit is zero that it does converge. That's what this is saying. But it does say that if the limit is not zero, then it for sure diverges. Okay, it's a test for divergence. If you do get zero, then you can say nothing. It might converge. But this is a quick way to check, like for example, in this series, that determine whether it converges or divergent. Here the series, okay, this looks funky. Let me see if this even approaches zero, the terms do. Take that limit and then that'll tell you whether it has a chance of converging or if it diverges for sure. Do you guys remember how to check this limit?
That's just because there's only two n values or whatever, you just get a like a fraction.
Yeah, exactly. Yeah, this is n to the first, this is n to the first. They will grow at a similar rate, meaning as you go to infinity, you'll just get the ratio of the coefficient. If you didn't remember that, then you could treat this like an x and do L'Hopital. You get the same thing. This limit is 2/3. Meaning I did not get zero for the terms, meaning this diverges. What? Why does this diverge if you just told me the limit is 2/3? No, the limit of the terms is 2/3. Meaning here, you'll add, here, let me plug in Chris Few. We'll be adding 5 over, what is that? -2 plus 7 over 1 plus, do one more. Plug in a 3. 6 plus 3 is 9 over 9 minus 5 is 4 plus blah, blah, blah. You keep adding in this way. And eventually each term is very, very close to 2/3. So eventually you add, and then you're adding plus 2/3, plus 2/3, plus 2/3, plus 2/3, plus 2/3. And when you see it like that, then it's very obvious. Oh, of course, this diverges because eventually you're just adding numbers. It's very, 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 very close to 2/3. That's why that diverges. Yes, this makes sense. Nice, y'all. Next one, I think I want to skip. I think that's the n factorial one. Yeah. First of all, n factorial. Do you guys know what that means? I'm going to skip this one, but do you know n factorial? You ever seen this? N factorial, like for example, 5 factorial. 5 factorial. Yeah, write that somewhere. God. Yeah, please just 5. Get out of here. Okay. 5 factorial. Something factorial is 1 times 2 times 3 times 4 times 5. Or most of the time, for whatever reason, the convention is to write it 5 times 4 times 3, like big to small. So that's how you'll see me write it eventually. But that's what factorials mean. And I'm not trying to get to that on the first day, especially when this is written kind of ambiguously. You don't know if it means 2n factorial or 2 times n factorial. Either way, you weren't supposed to get that this converges, I think. And so, like, I want to skip this for the first day. We'll see enough factorials later that I'm not worried about doing this one right now. Because taking the limit of that is also annoying, more annoying than it's worth. All right, and then this one.
You do like a C or 12, you'll always get like an N2 that's not. Right? Yeah, it would be like one. Yeah.
All right, this one, same thing. Let me check if this one even has a chance of converging by taking the limit of the term. If I do that, intuitively in your brain, you might see this and be like, oh, 3 to the n minus 2 and 3 to the n, those are growing at the exact same rate. So this must have like a limit of 1 or something like that. Formally, how would you show that? You could split the thing like this. And then you got something over itself is 1. And minus 2 over enormous thing. So this basically goes to 0. The 1 minus 0 equals 1. Cool. All right, and then I can say that what about this sum? Exactly. The terms get closer to 1, so eventually I'm adding 1 plus 1 plus 1 plus 1, which for sure does not this divergence by the end term. That says divergent. Nice. And then telescoping series, I was going to skip anyway because that's not on the AP test, and I don't want to.
Why is it not on the AP?
Just because they're very particular, specific type of sum where like terms in the middle cancel, you just get the outer term. It's kind of interesting, but not for when we have 3 minutes left, and I want to spend more time on the others. Cool. Okay, so that I wanted to skip this anyway, so we're done with 10.1, which is good news. That means we're a little bit ahead of where I wanted to be. But that doesn't mean no class tomorrow. Let's keep going, and then maybe we can cut days out of the end of the unit rather than the start. Nice, y'all.